Okay. So today is going to be kind of just, we're going to get through lecture and any questions you guys may have, obviously ask. But I am going to, conserve my energy as much as possible. So we are covering today chapter 8, which is hypothesis testing. Can you guys see this? Yes, thank you. I don't know why I'm on the last slide. Okay, here we go. And then I don't have both of my screens. I don't have my mouse. I feel like I'm naked a little bit teaching tonight. But we're just gonna do the best we can here, gang. Can you guys see? It says testing hypothesis in really big letters.
Yep.
Okay, awesome.
Yeah.
Okay, great. Before we move forward, there's no quiz today. The quiz will be next week. I think I had said that already last week, that there's no need to do a quiz on just one, week's material. And then if you need extra time for your confidence interval lab, please just shoot me a text or an email, and then I'm happy to extend that. Otherwise, it's due by midnight tonight. And it was just, I want to say Hannah brought this to my attention, that the prompt said more variables than the variables I'd given you. There's something confusing about it. Ultimately, just do what made the most sense, right? Like we talked about the variables that were on there that you need to calculate the confidence interval for. Does that make any sense? Sort of. If you have questions about the lab, I guess just reach out. Let's see people in the chat. Oh, that's totally fine. No worry, Liz. Okay. And tonight is my son's 11th birthday. It's kind of heartbreaking. Like, I did a FaceTime call. I'm like, Mommy loves you. I give you a hug soon. So sad. Okay, enough sadness. Let's talk about testing hypotheses. When we do research, we're often trying to figure out and answer a hypothesis. We have some idea in our head that's hopefully based on more than just a hunch or an opinion. It's based on literature and past studies. And then we decide to test it out. And the way we test it out is we take some sort of measurement, some sort of quantitative analysis of it, and then we run some analysis to either confirm or refute our original hypothesis. So what we're going to talk about today is exactly that. How do we create hypotheses? How do we test them out? And what does that look like? Specifically, we'll talk about t-tests tonight. So without further ado, this one just jumps right in. So one of the examples we're going to talk about this evening is in the price of gas. That is often known as an indicator of how well an economy is doing. So you see high prices of gas, economy might be more struggling, lower cost of gas, there's good availability of gasoline, good relationships with the Middle East oftentimes. So those two kind of go together. Now, why do we care about the cost of gas? Well, do you guys care about the cost of gas? What do you think?
Yes.
Why is that, Savian?
Because I mean, we need it to run our cars and just to run most of society.
Yeah, absolutely, right? So when do we see expensive gas prices? Have you guys ever noticed a trend?
Sometimes around holidays, there's a lot higher because most people are traveling.
Yes. I'm trying to figure out who just said that, and I can't see people's faces.
That was me.
Still don't know who that was. Hold on. Is it Hannah?
Yeah.
Okay. I just see boxes and they don't light up unless I'm.
Mine has the flower.
Yours has a flower? Why don't I see a flower? Oh, there it is. I was not sure what that was. Okay, good to know. So, absolutely. Whenever there's known travel period of time, either holidays, oftentimes during the summer, where people will go for longer periods of time, or people will go camping, prices of gas will increase because they know there's a greater demand, right? Now, what we know about socioeconomic groups is that lower income Americans spend 8 times more of their disposable income on gas than wealthier Americans. So the impact of gas prices will really impact the lower income groups because they're spending so much of their money already on it. So as an example, in Wilcox, Alabama, individuals spend 12.72% of their income to fuel one vehicle, while in this particular county of New Jersey, people spend 1.52%. Okay, now let's give another reason why we think in New Jersey they spend less on gas. What do we think?
Public transportation.
Yes, and that's spot on. So there are parts of the country that have very well developed public transportation system. LA is not that great, right? But New York is phenomenal. Chicago is a lot better. I don't know that I would say Grand Rapids is amazing or anything like that, but I would say no, right? But the parts of the country where there is better access to public transport, then people are going to be spending less on gas. Oftentimes they don't even have a car. So that's another portion of that. So nationally, Americans spend 3.8% of their income fueling one vehicle. And the first state to have reached $5 per gallon milestone was California in 2012. Now, similarly, I remember, so I lived in California for many years, and I remember gas being less than $1 also in California, not in 2012, like maybe in 1999 or 98. And I was like, oh, this is amazing price, because it had been a lot higher and then it dropped. But it goes up and down. But it is always significantly higher than it is here, for instance. All right. So in May 2016, there's a random sample of California gas station that was taken. There's 100 gas stations that were surveyed, and the average price was $2.73. Now, the national average for all the United States was $2.32. So when we see that discrepancy, we can start creating hypotheses. One could be that the average price of gas in California is in fact higher than the national average. Two, it could be that the average price of gas in California is actually the same as the national average, but that our random selection, our sampling method, may have led to some random chance or error. So that somehow we picked 100 random gas stations in California that were all near airports. And as you guys know, near airports, you just always spend more money, right? So that's my alternate hypothesis. So how do we determine which one is more likely to be correct or true? So we use statistical hypothesis testing. And here's what it would look like. It's a procedure that allows us to evaluate hypotheses about population parameters based on sample statistics, okay? So again, our population parameter here is that the national average price of gas is less than the cost of California gas, which is our sample statistic, okay? So the hypothesis is the average price of gas in California is higher than the average national price of gas. That is the research hypothesis, okay? So a few assumptions. We can assume that the sample was randomly selected. We have to have a variable that's measured at the interval ratio level. So for instance, we cannot do that if we're using a nominal data, right? Something like, are you a Republican or a Democrat, or your marital status, right? Those are not interval ratio items. We cannot assume that the population is normally distributed, but because our sample size is large enough, it's greater than 50, based on the central limit theorem, which we've talked about, we know that the sampling distribution of the mean will be approximately normal. So because of all of that, all of these assumptions, we can then set up this research hypothesis and set it up for statistical analysis. So first we make a statement reflecting the substantive hypothesis. It's a statement about the population. So it's always expressed in terms of population parameters, but its specific form varies based on the test that you're going to use for statistics. So for our research hypothesis, it's H1 or the alternate, right? That's H1 or HA is for alternate hypothesis. We state that the average price of gas in California is higher than the average price of gas nationally. Symbolically, we're going to use the mu to represent the population mean. Okay, we've talked about this before. This is what it looks like. Is everybody seeing? So this is this guy right here. Okay. So the average price of gas in California is higher than the average price of gas nationally. The price of gas of the population of California is greater than the price of gas of the population of all other states. So our H1 or our alternate hypothesis or our research hypothesis is that the mean is greater than $2.32. Okay, that is the national average was $2.32. And we're saying that the mean is going to be greater than that in California. Okay. Are we following so far? Or am I going too fast? Is this all making sense? If it's not, somebody stop me. Otherwise, I'm going to keep on chugging until I start choking. Okay. So let me minimize our faces here. So the research hypothesis specifies that the population falls in one of the three categories here. So it can either not equal to some specified value, right? Mu does not equal whatever it would be. It could be that it's greater than or less than some sort of specific value. Okay, in our example, we're saying it is greater than a specific value. But it's possible that you may not know which direction it's going, which is when you would use this first one. You're saying, I don't know if it's going to be higher or lower, but I don't think it'll equal this other value. Okay, so that's the difference between directional and non-directional hypothesis. This is a non-directional hypothesis. These two are directional hypothesis. You are staking a claim as to which direction you anticipate it'll fall. Okay, so we talked about the research hypothesis or your alternate hypothesis, right? Now, this is the null hypothesis. A statement of no difference that contradicts the research hypothesis and is always expressed in terms of population parameter. That is the null hypothesis. It is expressed as H sub 0, which is for null. And then it's some, the mu, the mean, is equal to some specified value. That value, again, can be any interval ratio number, including 0. So it's possible that the population, that there's no real difference between the mean price of gas in the nation and in California. It is absolutely possible. So under the null hypothesis, the observed difference of 46 cents between what we found in California versus the national average is actually due to the fact that our sample happened to contain California gas station with higher prices and is not representative of the state, just like I was saying earlier. This could be due to, error, right? So I need to have the possibility that there is no significant difference, that the price of gas in California is not in fact higher than the national average. Okay. So since statistical inference is based on probability theory, right? We talked about that because we end up, you guys remember when we were talking, I'm gonna get my pen out here. We talked about P, oh, whoa, this is gonna be hard without a mouse. Oh, okay, that's a P, less than 0.05, okay? What does that mean again? If we say that the P is less than 0.05. Ooh, that's fancy 5. What does that mean?
I know it has to do with probability, but I don't remember specifically.
Right? So you're on the right track, Hannah. So when we see a P is less than 0.05, that's indicating a significant result, right? So that means whatever the statistical analysis that was done prior to that, we feel it is not due to random chance. In fact, the chances are that the difference we found that is due to chance is less than 5%. That's the amount of error that we are allowing within our statistical analysis. Okay, so if you see something like that, that means let's flip it upside down, right, with our confidence interval. This means I am 95% confident that the results we got were due to an actual phenomenon between these variables and not due to chance. Okay, so that is inferential statistic. And because it is based on probability, it is not possible to prove or disprove a research hypothesis. So this is just something you guys need to remember. When you are going to write your conclusion statement, which you'll need to do for any hypothesis testing result, you cannot say, I proved that the research hypothesis was correct, or I disproved the null hypothesis. We are not using the word prove at any point. You can say you fail to reject the null hypothesis, or you reject the null hypothesis. So we'll talk about that again in a minute, but the word prove should never be part of that. Okay. So what we're doing is we're estimating the likelihood of what is true or false. So we set up a hypothesis that is counter to the research hypothesis, and that's what's known as the null hypothesis. So we come up with our idea, our research hypothesis, and then we do the exact opposite, and that becomes our null. If in null hypothesis testing, we hope to reject the null to provide indirect support for the research hypothesis. What we're doing is we're testing the null hypothesis. We are not testing the research hypothesis. We either reject or fail to reject the null hypothesis. So if you reject the null hypothesis, that implies that your research hypothesis was more supported, okay? It's kind of a funky thing that we do it backwards that way, but that's the way statisticians have been doing it for years, so. All right. All right, there's what's called a one-tail test. That means it is a directional hypothesis testing. So it's a hypothesis test in which the alternative is stated in such a way that the probability of making a type 1 error is entirely in one tail of sampling distribution. Now hold that thought. We're going to talk about type 1 error in just a minute here. But what you need to know is that in one tail test, you are saying, hey, gas is going to be greater than this amount. So that's where we're looking for it to fall. So if there's an error, it's going to be in that tail. And the tail that we're talking about is our normal curve. In fact, okay, here we go. Okay, remember z-testing? Shake your heads yes, because that was not that long ago, right? Okay, so if you did one tail and we're like curious as to stuff that's in this tail right here, shoop, that would be essentially what we're doing with a one tail test. We are only testing out that tail of the normal curve right over here. Okay, so again, if my research hypothesis is that the mean is greater than $2.32, then I'm saying it's somewhere out here. Okay, So as I mentioned, it involves a directional research hypothesis, and it specifies the values of one group that are either greater than or less than some specified population value. Okay, so as I've mentioned, testing the price of gas is a one-tailed test as well. Okay, so you may have a right-tailed test or a left-tailed test, and it just depends on the directionality. A one-tailed test in which the sample outcome is hypothesized to be at the right tail of the sampling distribution means it's typically greater than a specified value. That's what I was just showing earlier, right? The price of gas. Left tail is if it's going, you're suspecting that it's going to be less than a specified value, then it's going to be the left tail. The region of rejection of the null hypothesis is in one tail only, okay? So these tests are less stringent or strict than two-tailed tests, which are by nature more conservative, stringent, and strict. And how do we know that? Why would a two-tailed test be more strict?
Sorry about that.
No, it's okay. I just didn't hear. All right, let's do a little drawing. That's always helpful to me. Although my drawings are crap tonight because of my trackpad. Whee! Oh boy, this is very bad. Okay, one-tailed test. So if I am looking for a p-value of 0.05, where is the error going to be found? Where is that 0.05 located?
In the right tail?
Yes. So it would be all contained right here. Okay. Now, in a two-tailed test, it is still 0.05, but where is that located now? Where's the error? If I don't know if it's greater than or less than, where is it?
In the left and right tails?
Correct. So if I do not know the directionality, then it could be either tail. I'm saying I don't know, right? I just don't think it's the same price, but I don't know if it's going to be more or less. So now I also have 0.05, but is it 0.05 on either way, on either tail? No. Why is that, Diana?
Because it's split in half, so they would be 0.025 on each.
Exactly. So you have to do this divided by 2. Okay. So, oh boy, I'm going to struggle writing 0.025, but 0.025. My fingers are going to need a break tonight. So that's 0.025. And this over here is 0.025. Those are much smaller regions, right? Much smaller than this guy over here. That's 0.05 for just one side. Okay. That is how it is more strict. It's more stringent and it's more conservative. Okay. Okay. I want to make sure everybody's had an opportunity to kind of digest this. Doesn't make sense. Questions I can help answer about that. Because you guys need to, that's kind of a key point. No? Everybody's good? Okay, we keep on trucking. All right, two-tailed test. Oops, maybe somebody was writing a question in the chat. Oh, thank you, Lainey. All right. So a hypothesis test in which the region of rejection falls equally within both tails of the sampling distribution, that is what's called a two-tailed test. These tests are more stringent. We may have some theoretical basis to believe that there's a difference between the groups, but we cannot predict the direction of that difference in one way or the other. So another reason why you would use a two-tailed test is to get a result opposite of what you predicted. If that happens, you use the one-tailed test, even if you have significance in the opposite tailed, your results will be inconclusive. So that's another way that you could try to manage that as well. Now, I know this says SPSS. In our world, Excel will also give us a two-tailed test by default. You will need to select, when we do our lab for the t-test, we'll have to select one sample t-test or one tailed test. I'll show you guys how to do that. But this is what the research hypothesis would look like. It would say that the mean does not equal $2.32. And then our null hypothesis could be that the mean is equal to $2.32. Okay. So if you want a one-tailed test, you need to divide your p-value by 2, which becomes a p-value of 0.031. That's analysis we can talk about in just a minute. There we go. Okay. So if we're using an alpha level of 0.05 in each case, and I kind of just described that a minute ago, this is what it would look like. Okay. So if it's to the left, the dark blue area is 0.05 of the total curve. Again, this is 0.05 of the total curve on the right side. On the other hand, if we look here, if we have a two-tailed distribution, we have to split it 0.025 on either side of our tails. Okay, so it's a smaller area. So you can see the shaded area of the tail is where our statistic would need to fall in order for it to be significant. With both tests, our null hypothesis of no difference remains the same. Okay, much nicer drawing than my little chicken scratch. But okay, so let's look at probability values again. We are assuming that our null hypothesis, oh gosh, I'm so sorry, you guys. Hold on, my kids are asking me questions. They are all good. Okay, so we're assuming that our null hypothesis of the mean is $2.32 is true, right? We're going to say that that's the mean, and we want to determine whether our sample evidence casts doubt on that assumption, suggesting that there is evidence for the research hypothesis of the mean is greater than $2.32. So again, we're comparing these California prices to the national average, and we're saying that the mean has got to be higher than $2.32. Excuse me. So we can use a z-statistics first, which we know how to do. So the test statistic computed by converting a sample statistic to a z-score. And we know this for the population versus a sample. We've done this before. And we can also calculate the p-value, which is the probability associated with the obtained value of z. We can also look at this with the probability associated with obtained value of t, f, and r. Okay, so t-test is what we'll talk about today. We are going to talk about the f-test later on, and r, that's a correlation or a Pearson R test. So any inferential test, we can use a p-value, and we can use that to test hypothesis. All right. So we're going to assume that the null hypothesis is true, and we will see if our sample evidence casts doubts on that assumption. So we have a sample or population mean of $2.32 and a given standard deviation of 0.17. Our sample size is 100, and the sample mean was $2.78. Now, all of these numbers, guys, are just given, right? They were at the start of the lecture. The only thing I'm just adding now is the standard deviation. We can assume that the distribution of all possible sample size is drawn from a distribution that would be approximately normal. And so we would plug in our values right here, which would give us the standard error of 0.02. We would then plug in all our values. So converting a raw score into a z-score, you guys remember how to do that, right? We take our value minus the mean divided by that standard value of standard deviation. Because we're doing hypothesis testing and we're dealing with the sampling distribution in which our raw score is the mean and the standard deviation is the standard error. So we plug that in using this formula. All right, let's go back to doing some fun math here. So plugging in my formula, I have my gas value, right? This is my sample mean for California gas prices minus my population mean, right? I'm assuming this is my population mean, which is the national standard for gas prices. 0.17 is the population standard deviation divided by the square root of my sample size, which is 100, which gives me a score of 23. All right, our Z statistic is pretty massive, right? Just that right there, 23, you should go, whoa, that seems kind of big. Because if we look in any of the charts you find online, the top Z score only goes to 4.5. So you'd be like, no, that's do not pass go. Something's not right. So what do we do? Well, we can say that, again, Z somehow is so far over here that our p-value would be super, super tiny. That's not going to be quite meaningful, though. So Z-tests follow the normal distribution and do not rely on degrees of freedom like a t-test. And this is where the t-test becomes very powerful. With a t-test, first off, we can set off our alpha value. Now, we've done this before with the Z-score. Remember, we talked about you're always going to use 0.05 for the most part, magical Z-score of a 1.96. Remember, we talked about all that. So again, it's going to be customary for us to set the alpha at 0.05. That's going to be the most common one you use. They are arbitrarily constructed. We need to be aware of that. But that is where we go. That's what we use. So we're not going to poke too many holes at it. So if our p-value is smaller than the alpha, we reject the null hypothesis. Meaning if the result we get falls in that critical area of under our curve, under that tail, it is safe for us to say that we reject the null hypothesis, that there is no difference, or in this case, that the price of gas is the same as the national average. Okay. If our p-value is greater than the alpha, meaning it falls outside of that critical range, right? It's not in the tail, it's further over, then we fail to reject the null hypothesis, meaning at this point, we don't have enough evidence to support that our research hypothesis would in fact be true. So the alpha level is our level of risk. It's the amount of error we are willing to accept when we're doing that statistic, when we're running the analysis. Okay, does that make sense? Okay, so you set your alpha level, and if your p-value is greater than your alpha, you fail to reject the null. That's the biggest piece. If the p-value is smaller than your alpha, so an example of a smaller alpha than 0.05 would be 0.04, 0.03, 0.01. All of those, excellent. That means we reject the null hypothesis and we can feel more confident, again, with a small amount of error, possible error, that the results we got were because of a genuine relationship between these variables and not some random chance. Confirmation. Okay. All right. So 5 steps in hypothesis testing. First, you start by making your assumptions. Again, hopefully you're not drawing those out of thin air. It's based on research. It's based on data you have. Next, you have to state your research hypothesis and your null hypothesis and select an alpha. Now, this last one, selecting an alpha, it should almost 99.9% of the time will be 0.05. So don't lose sleep over this, right? Next, you're going to select the sampling distribution and specify the test statistic. Sometimes you might use a z-test. Most often we'll be using a t-test. Then you compute the test statistic and you make a decision and interpret the results. Okay, so you always loop it back to your original research and null hypothesis so you can make a statement as to what are your findings. All right, we're going to dissect all of that again with the example of the price of gas. So making assumptions. So we're making assumption as to the level of measurement of the variable, sampling, the shape of the population, all of that. We talked about this already a little bit. Random sample was used. The price is measured as an interval ratio, so that matches. And because our n is greater than 50, it's 100, we can have an assumption of normal population that's not required. Okay, here's how I would show my research and null hypothesis. My research hypothesis says the mean is greater than $2.32. The null hypothesis, which contradicts this research hypothesis, says there's no difference between the population mean and our sample mean. Okay, so that would be, no, actually the price of gas in California is in fact $2.32. We would set our alpha at 0.05, meaning that we would reject the null hypothesis if the probability of our z-score was less than 0.05. Okay, so I've just set my alpha. Okay. Next, I would select my sampling distribution. In this case, it's a normal distribution. We thought we'd use the z-statistic. We computed it as we just did a minute ago. Our z-statistic was 23. Now we make a decision. We confirm that our z-score was on the right tail of the distribution. In fact, it was massive, right? It was really, really itty bitty at the end of the tail. And we determined that the p-value was less than 0.001, which inherently, this number is smaller than this number. So it's less than our alpha level, which means we can reject the null hypothesis. California gas prices are significantly higher than the national average. And I would write it with this word in it because this shows that it is a statistically significant result. Okay. Questions, comments, concerns? How does this jive? It's good, it's all making sense? Must be feeling better than I thought. Maybe I'm more coherent. Okay. All right. Just looking through, got a few thumbs up. Great. All right. All right. Remember a minute ago, I was like, hang on to that type 1 error. We'll talk about it in a second. Here it is. So whenever we run hypothesis testing, we're also evaluating the risk of making errors, okay? I feel like we've talked about this in this class with specificity. Did we talk about specificity and sensitivity? Or is that in my research class? That's not sounding, it's not ringing a bell. Okay. So type 1 error is the probability associated with rejecting a null hypothesis when in fact it's true. So that's what's considered a false alarm or a false positive, okay? It's a, oh, just kidding, you don't actually have cancer. Yay, good news, right? Okay, so that is a type 1 error. That means our test was likely so sensitive that it picked up levels that were not, in fact, within our required threshold, okay? So this is what I wanted to hope for with this COVID test. And it turns out, no, it was real. In fact, I'm wondering if my first test was a type 2 error. It's the probability associated with failing to reject a null hypothesis when it is false. It's the failure to detect a difference or a false negative. It's a just kidding, actually, you do have cancer. We didn't catch it the first time. So that is a test that is too specific, that we may end up missing. It's not sensitive enough, it's too specific. So we may miss some positives in there, okay? It's a false negative. Okay, so type 1 and type 2 errors are inversely related. If you reduce type 1 error, you conversely increase your type 2 error and vice versa. When we run statistics, we are trying to minimize both. But there are times, like if you think about medical research, where they may be more okay with one type of error than the other. And test makers, like biological test makers, have to make that choice. What is most important? If it's protecting the public, maybe I'm okay with some false positives, and I would maybe prefer that, especially in a pandemic area, than having some false negatives and run the risk of somebody spreading a contagious disease, right? I would rather say, hey, just kidding, your test actually came back positive the first time around, but it wasn't. But now, hey, yeah, you quarantined for a little while, but at least we didn't put people at risk, versus the other way around, and you don't have a very sensitive test and you're like, oh no, you're fine, you're fine, you're fine. And it's spreading like wildfire. Does that kind of theory, does that make sense? Okay, we use the same thing when we do statistics. Obviously it's on a different scale than like medical research, but it's the same idea. All right, so this is going to be a handy dandy chart. There will be a question on the exam on type 1 and type 2 error. So I would recommend you remember this chart. All right, so this is the true state of affairs, and this is the decision that you made, okay? If in fact the null hypothesis is true, but you rejected it, okay, that is a type 1 error. If the null hypothesis is false, but you did not reject it, that is a type 2 error. Obviously, both of these are the boxes we want to live in. Those are the correct decisions, right? These are the errors. Okay. This here, type 2 error, is also known as beta. You don't need to worry about that so much. This is alpha. Yeah, not a big deal. All right. Let's talk about the t-test real quick. The t-test is a test statistics that's computed to test the null hypothesis about a population mean when the population standard deviation is unknown and is estimated using the sample standard deviation. Okay, now let's think about this for a second, because when I provide you guys with example and I give you the population standard deviation, it's fine and dandy to plug it in the formula, but stepping into the real world, how, like most often we don't know the population parameters. We don't know the population standard deviation. This is far more likely where you have a sample statistic, like your sample mean, and you have a sample standard deviation, and then you use those two to approximate the population. So that's why the t-test is so powerful, is that it's far more real life and real world than kind of the make-believe world is the z-test, where you're just given, right, a standard deviation. Now, this is for a one sample t-test. Okay, and we'll talk about the difference between two sample in just a minute. Okay, so okay, so for a one sample t-test, we use this instead of the z-test when the standard deviation of the population is not known. And what we do is we use this degrees of freedom, which is the sample size minus 1. Okay, that is one way that we reduce that number to, I don't know why we use degrees of freedom, honestly, but that is what we do. So we're going to stick with that. Okay, so the t-distribution is a family of curves, and each is determined by its degree of freedom. It's the number of scores that are free to vary in the calculating statistic. Again, that's going to be your sample size minus 1. We use this when the population standard deviation is unknown. And it's important between, one major difference between the Z and the t-test statistic is the the standard deviation is estimated from sample data, and the denominator of the t-statistic is subject to sampling error. Okay, this is what the formula looks like right here. And let's look at these different curves. Okay, so these are the curves. This is a normal curve here, that solid bar. And then you can see with degrees of freedom 20, degrees of freedom 5, and degrees of freedom 1. So you see how the curve is varying. It is not a normal distribution for all of them, right? So we can't use the standard normal distribution because of it. All right, so let's do an example because that always makes things a little better, I think. All right, so we have a random sample of 280 white females who worked full-time in 2014. We found that their mean earnings was $41,653 with a standard deviation of 29,563. Right off the bat, what do we notice about these values?
The standard deviation is very large.
Okay, and what is that suggesting, Diana?
That there's a lot of variation.
Yes, there is a lot of variance in our sample of 280 right there. Excellent. So based on the data from the Census Bureau, we also know that the 2014 mean earnings nationally for all women was 39,621. But we don't know the population standard deviation. We don't have that information. So we want to determine whether the sample was representative of the population of all full-time women workers in 2014. In other words, did these values in our sample of 280 females that gave us these sample statistics here, does that jive with the census data, which tells us that the mean income is 39,621? So that's our question. Okay, so we go down the exact same way that we did earlier with hypothesis testing. So first, let's make some assumptions. We're going to assume that we use a random sample. Because our N is greater than 50, we don't have to worry about normal population requirements. And then the level of measurement is income, which falls as interval ratio. Okay, so here's our two hypotheses. Okay, so our research hypothesis or alternate hypothesis is that the mean is greater than 39,621, right? Our null hypothesis is that it's exactly the same. It's exactly the census value that was received in 2014, that it would be equal to 39,621. And then I set my alpha at 0.05. Okay, I want to make sure I don't miss any of your faces if you have any questions. That's all tracking so far? Okay. Next, I select the sampling distribution and I specify which test statistic I'm doing. So we're using a t-distribution and we're going to be running a t-statistic to test the null hypothesis. Okay. Let's minimize your faces now so we can do this. So we calculate the degrees of freedom associated with our test, which is 279. We'll get back to that in just 1 second. Next, we calculate T, which is my sample mean, 41,653, minus my population mean, right? That's my Census Bureau value of 39,621, divided by my sample standard deviation, 29,563, divided by the square root of my population, which is 280. That gives me a t-value of 1.15. Okay, now hopefully right now you're going, okay, what do I do with 1.15? What does that mean? Okay, well, we have to go and figure that out. So to determine the probability of observing a t-value of 1.15 with 279 degrees of freedom, we have to refer to our t-table. There's a T table in the back of your book, the same as the Z table. It's just a little further over. I think it's the very next appendix. Or you can look it up on search Mr. Google for a T table and you get the same thing. Now, using the first column, you have to round up to the degrees of freedom that are closest. So you'll notice the degrees of freedom vary quite a bit. The closest one for us will be 300. So now our question is our T statistic larger than our critical value? Now I wanna, did I add that? No. So let me just pull it up real quick. Here. Because I wanna make sure you guys get to see. Oh, I can't minimize Zoom because, okay. Let's do, well, all of you guys take a moment, open up a browser and T statistic table. Open that puppy up. You should get like gazillions that pop up. Just find one I can make big here. Are you guys finding one? And anybody?
Yeah.
Okay. I want to make sure, I can't get this to be bigger. What's the problem with me? Okay, I can share this one. Whoops, where are you guys now? My computer's not liking how many apps I have open all at once. Okay, here you are. Shoot, why won't it? Grr. I'm not certain what's happening, but oh, okay. Let's try again. Yes. Okay, can you guys see this chart? Yep. Okay. Thank you. Minimize your faces again. Can't see anything. Okay, so you can see here, this is degrees of freedom. So I would go down the line till I find I'm looking for 279. This is not a great table because obviously there's a mega jump right here between 100 and 1000, which is kind of problematic. Now I know I want to stay at the 95% confidence level. If I go back up here, it'll show here. This is the cumulative probability, and I want to be at T.95, which hopefully that, I don't know why that's different, but yeah, we'll stick with this one right here, 0.05, right? That's what we're looking for. Or if it's one-tailed, we can look at 0.025. Okay, and what was our value? We got 1.15. Was that right? Anybody remember? Pretty sure that's what it was.
I'm pretty sure it's that.
Yeah. Okay. So then my question is the value that I'm getting, does that fall in the critical region that would make it significant? And it looks like it would be somehow between 1.984 and 1.962, according to this table. Okay. Does 1.15 fall within that value? What do we think? So in other words, because I think somehow I'm making this tricky and now my iPad's ringing. I'm not trying to be tricky. Let's see, can you guys see this I'm writing? Okay. Okay, this is saying, whoa, this is by far the worst one, gang. Okay, this is saying for my one-tailed test that the value, in order for it to be significant, right, needs to be at least, this lower value would be whatever that was, 1.96. Okay. But my actual value is further over here, 1.15. So what do we do? Here, let's go back to our survey, our lecture. Okay. Is our T statistic larger than our critical value? No. Okay, good. Hopefully you guys are all seeing these numbers. Okay. So we would say that it's not, and we fail to reject. The values are too close together in order for us to feel confident that the results are not due to the random chance. Okay? Is that adding up for people? Okay.
Yes.
Okay. There's a different test that you can do. So I'm switching gears a little bit. That was the one sample t-test. You can also have a difference between two means. So you can have two groups and they have two different means, and you want to know, is their difference between their means, is that significant, right? So this is a common one that you can do for a t-test if you're looking at gender. So I'm curious as to academic performance between males and females. Maybe I calculate everybody's GPA on one side for one group of women, another side, one group of men, and then I compare them. And I ask myself, is this due to random chance, or is it because there's actually something happening? So that is called an independent samples t-test. Each participant is only in one of two groups, and it is different than a paired sample or repeated measure design, which we'll talk about later. So you would be comparing the sample mean of your group 1 minus sample mean of group 2 and divided by the standard deviation of group 1 minus group 2, okay? And the question is the value significantly different from 0? Meaning, is the difference between the groups greater than 0, meaning they're not the same? Okay. So this is similar. This is the GSS, the Global Social Studies survey of 2014. So this is testing about differences between two sample means based on the sampling distribution of the difference between means. So I've got a sample. This is years of education for white and Black men and women, okay? So it's divided by racial group. And we found the mean was 13.88 with a standard deviation of 2.99 for whites. And for Blacks, it was 13 with a standard deviation of 2.28. Now, notice the standard deviation, the population size or sample size are very different one from the other. So that is going to play a role for sure. Okay, so we run through the exact same thing. First, we can make the assumption that independent random samples were used. The variable years of education is an interval ratio, so that works. Now, this here is an error because, oh no, it is 88, so that's fine. So both are greater than 50, so we're good to go. We don't have to deal with normal population requirements. Okay, next, we state our research and our null hypothesis. So our research hypothesis is that the mean education of Caucasians is different from the mean education of African Americans, which indicates a two-tailed test. I'm not saying which direction it is, I'm just saying it's different. So the research hypothesis is that the mean for group 1 does not equal the mean for group 2. It doesn't say a directionality, just it doesn't equal it. And then the null hypothesis says, no, they're equal, they're the same, okay? For this, I'm gonna use a t-distribution and run an independent samples t-test. And here's how I would compute the statistic for it. You start here. This is your sample size -1, so you've got your degrees of freedom, times your standard deviation squared, plus the sample size for group 2 -1 times their standard deviation squared, divided by both of their sample size -2, because again, you've got to make sure that you're taking away the 2 groups, okay? And that gives us a standard error here of 0.35. Now I plug this information in right here, which tells me then the mean of group 1 is 13.88 minus the mean of group 2, which was 13, divided by my standard error. This is what we calculated over here, which equals 2.51, okay? Now, I really struggled to pull up that chart again a second ago. So you guys would have to pull that up. Again, we're looking at degrees of freedom of 531. And here's how you do it. You add both of their sample size -2, because you've got 2 groups, and that gives you 531. So based on the number we got earlier, because we're still using 95%, it was like 1.962, if I'm remembering correctly. That would be our critical value, okay? So does 2.51 fit? Is it bigger than the critical value?
Yes.
Yes, okay. So what would be our decision?
We
The-
reject the null.
Yes, exactly. So our decision is to reject the null because it is bigger. All right, so here's how we would write it. If you're using APA style, which you should, and when you look at reviews or articles, this is how they'll write it. A two-tailed independent sample t-test revealed Caucasians, and you would include the mean and standard deviation, had significantly more years of education than African Americans, and you include the mean and standard deviation. And this is where you include the statistics we just ran. It would be a T statistic with your degrees of freedom, 531. This is the result we got, 2.511, and the p-value is 0.12. Now this p-value, gang, we are gonna figure out how to calculate that in Excel. You do not need to calculate that by hand. So when possible, you want to give the exact p-value and round everything except the sample size and degrees of freedom to the thousands place. That's the goal. Okay. Let's use another example. So we're doing hypothesis testing with a 2-sample proportion. Maybe your question, what you're deciding to research, is there a difference in education as a function of whether you were born in America versus born in a foreign country? Maybe you're curious about that. So the proportion of first-generation Hispanic Americans who earned a bachelor's degree or higher was 0.11, okay, or 11%. The proportion of second-generation Hispanic Americans with the same response was 0.21. There was a total of 899 first-generation Hispanics and 351 second-generation Hispanics. So now we have our proportions and we have our sample size. Now let's look about using a Z-test and why that might make the most sense. All right, so z-test, we have used that before to use proportion. Our research hypothesis is that the two means are not equal to one another, okay? That there is a difference between the two, whether you're first generation or second generation. Your null hypothesis is that there is no difference. They're exactly the same. So the way you would calculate that is first, we need to find our standard error right here. We do a ton of calculations here with our proportion. I swear we did this last time. Hopefully you guys remember that for confidence. So proportion times 1 minus the proportion divided by the sample size. Same thing for your second sample. Let me move our faces because I can't see the numbers, which gives you a result of 0.02. Then you plug it in right here. This is our proportion, right? So 0.11 minus 0.21 divided by our standard error, which is 0.02, which gives me a result of -5. Okay, now we know for Z statistic, that's going to be well past our critical value. Okay, so whoops. So the decision would be to reject the null that they are the same, that they're in fact not the same. Okay. And again, you could figure that out by going to your Z chart, which would show you that that is a significant value at the 0.05 level. All right. Now this here is SPSS. We are not doing that obviously for this class. And we've talked about how that mimics a confidence interval. Okay. Okay. This is key right here. The Z and the T statistic are very similar. Remember, we use the T statistics if we don't have a normal distribution or if I don't have my population standard deviation. Those are the two main reasons why we use it. But as N gets larger than 50, the T distribution really converges with the Z distribution. So the results should be practically identical, whether you use T or Z, okay? So that's another key point. There's obviously some analysis that we have to use a T-score. Like if you're looking at a difference between two means, we can't do that with a Z-score. We can just look at standardized scores. But the greater your sample size, the closer it's going to approximate a Z distribution and a normal distribution. Okay. Okay, this is difference in wages. This is a T-score. We can run through this example. This is men and women, and this is the mean pay that they get and the standard deviation for each. So you could see here, this is your mean for group 1 minus the mean for group 2. This is the way you would calculate here your standard error underneath. So you're doing standard deviation squared divided by the sample size, standard deviation squared divided by the sample size. Let's move our faces. That gives a T statistic of 1.23. You would then again verify that against the total degrees of freedom. I feel like this slide is missing some, this lecture is missing some slides for some reason. So you would then compare this 1.23 T value against the T critical at 0.05, which we know again for this group, it would be in the hundreds because this is exactly 100, right? 100 minus 2, so it'd be 98 for my total degrees of freedom. So it would be a little higher than that. It might even be close to $2, a critical value of 2. So this would fail to reject the null hypothesis because this value is smaller than my critical value. Okay, this is a chapter that is worth revisiting and looking through in your textbook. The main takeaways, you need to know what is the difference between a one-tail test that has directionality, like a right-tail test or a left-tail test, versus a two-tail test that does not have directionality. You need to be able to come up with a null hypothesis and a research hypothesis and know how they are different. And you need to know how to take the steps, just like we went through, where you first set out what is your research hypothesis, you write them all out, right? Set your alpha, and then actually run the statistic, and then make a decision based on it. Write out what the result is, and do you fail to reject, or do you reject the null? And then what does that say? What do the results actually mean? Okay, so those are the two biggest ones. And then remember to review your type 1 and type 2 error. That is going to be on quiz/exam. Okay. Okay. Questions, comments, concerns? A lot of stats meat we just went over. No, quiet. It's just so quiet tonight. Okay. Next week, we are going to be working on a lab where we practice these in Excel so we can start messing with them a little bit, getting some data from it. Next week is also a quiz, so make sure you log on right away, open up the quiz. We're going to do that first 20 minutes of class, and then we'll start lecture again. Okay, students asked me in my last class if we will still have class the week of Easter, and we will. Easter's on a Sunday, our class is Wednesday, so I just would hate to miss more time with you guys, so we'll still have class. If you guys have something going on, vacation plan or anything, just let me know. And then you obviously will have access to these recordings once it's done. Okay. No questions? All right, I'm gonna go pass out now. But you guys have a great rest of your night, and I hope to be in much better shape next week.
Feel better.
Thank you so much. All right, you guys, have a good night.
Good night.
Yeah, thank you, Professor. I hope you feel better.
Thank you.